Thank you for having us here. I am David, and I'm heading the Intelligent Information Agents group at the Computer Science Department at Bar-Ilan University, and I'm going to talk to you today about the autonomous helpers. So basically what my group is doing is game theory stuff, mechanism design, intelligent user interface, some work on robotics, and we're trying to combine all these two systems eventually. So autonomous helpers. So up until, for centuries, people have been used to receiving advice or guidance from other people. So this could be family members or experts such as doctors or mechanics or fortune tellers or wise men. And a few years ago, something has changed. People started receiving advice and guidance from autonomous helpers, right? So what are autonomous helpers? These are intelligent interfaces or systems that are designed to support people in daily decision-making or daily tasks, right? So it doesn't necessarily have to be daily tasks. It can be rare tasks, but still, they are supporting people. I'm dividing these into two categories. The first is agents that are designed to provide an advice or a suggestion. So here we can find systems that will tell you what music you would probably like or what you should listen to or how to get from point A to point B or what videos to watch, or even when to buy something. Is it now a good time to buy, or should we wait because prices are likely to change? And on the other group, we find systems that are acting on behalf of the users. So these are actually performing the task that the user needs to perform. So here we find mail filters, autonomous mail filters, or we can find here an autonomous car, or even the autonomous vacuum cleaner. How convenient. So the key for all these autonomous helpers is that we have an interaction between the autonomous helper and the user. So where does AI comes in? So some AI technologies were developed in order to help the system produce the most valued advice. And we have here some examples. We want to search better in the solution space. We want the finer classification or a more effective processing of big data. Other AI technologies are meant to support the interaction itself, right? So we want to communicate the advice more effectively or to facilitate interaction with the user. So here we can find gesture recognition or free speech technology and such. And other AI methods are meant, again, to support the interaction in the sense that they will provide us a more secured or a better understanding of what the user actually needs. So we have all kinds of attentional modeling for what the user is doing or methods for devising goal recognition and such. But still something is missing. There is something is missing in this puzzle. And the missing piece is the understanding of the fact that the user is often irrational. And this is not something new. We have learned over the years that people are often inconsistent, that people's decision-making is affected by all kinds of psychological effects, and they're often computationally inefficient. And there are tons of examples for this in psychology and experimental economics research. And this means that something needs to be adjusted or something needs to be changed, because these are very good techniques for producing a good advice, but the user is not necessarily going to follow the advice if he thinks this is not a good advice, right? So what my group is doing is the following. We are trying to manipulate these techniques, to change them, to mold them in a way that the advice we are producing is more effective if keeping in mind that the user is human, okay? Just to give you an example, here are 3 possible routes that my GPS based navigation system can generate to provide its user, right? So let's start with this route. This is the optimal route, right? Because it is minimizing the time I need to get from point A to point B. But this route is kind of shocking to people. If the user gets this suggestion, most likely he will think that something went wrong with the system. It is too fuzzy. It doesn't make sense, even though it is associated with 20 minutes, right? So the chance that the user will be following this advice is relatively low. Then we have this advice for going straight up until here and then to the destination. And this thing is associated with 26 minutes. This is quite intuitive. Most users are likely to follow this advice. But this is not what we want to give the user, because this is a very long route, right? And then we have this middle option, which is still a bit non-intuitive to people. But most people are likely to follow this advice. And if we consider the probabilities of following the advice, and if, for example, we assume that this will be the fallback route, so if a user doesn't listen to the helper, then this is what the user will do, and we do the math, then this is actually the advice we want to provide the user with. This is the most effective advice, okay? So I will present to you 4 challenges. Hopefully, I will have time for all of them that are trying to help understand how to design such autonomous helpers, given the fact that the user is often irrational. And I will start with the challenge of keeping in mind the intuitiveness of the advice given. So for this, I want to introduce you to an infrastructure we are using quite often in our experiments. It is called the car purchasing game. It has been used in prior literature extensively, also known as acquiring a company game. We have a buyer and a seller there, and the game is asymmetric in the sense that the real value is known only to the seller. So this is what the game looks like. We want to buy a car, right? So we go where? To the car dealer. And the car dealer is offering us a very specific car. We don't know the value of the car. The value can be anywhere between 0 and 1,000. So we have a uniform distribution here. This is all we know. We don't know the exact value. We just know that it can be anywhere here, right? Fortunately, we have an uncle who is what? A mechanic. And he tells us that he can take the car, and whatever the real value is, he will improve the car such that the new worth of the car will be 1.5 times the real value, right? So if the real value is 500, it will make it a car that is worth 750, right? And if it is 1,000, then it will be 1,500, okay? So good for us. We have such a great uncle, right? So now we have the dealer who knows exactly what is the real value. And again, it can be any value within this range. And we need to make an offer, right? And it will be a take it or leave it offer. What is a take it or leave it offer? If we offer above the true value, then we have a deal. If we offer below the true value, then there is no deal. How much should we offer? Anyone knows the answer for this? This is a very famous one. How much should we offer? Just throw whatever number that comes to your head. What? Whatever. Okay. So if you ask people, most people will say somewhere between 750 and 1,000. And very few will say less than 500 or 0. You want to know what is the expected profit maximizing offer here? It's 0. You should offer 0. Okay? You don't want to buy the car. And there are many explanations for this. We can easily do the math and see that whatever offer you are making, you are losing in terms of expected profit. This has to do with the winner's curse. But my point is that this is very non-intuitive to people, okay? And in fact, if the mechanic can improve the car's worth by up to 100%, so it's a factor of 2, then you should always offer 0. And if the mechanic can improve the car's worth by more than 100%, which is a factor of 2 and more, then the optimal offer is actually 1,000. And this is, again, very non-intuitive to people because it means we opt not to buy the car, despite the fact that the car is worth more to us than to the seller. Okay? It is also very confusing because there is a sharp transition here in the optimal strategy from offering 0 to offering 1,000. And this is very confusing to people. So here, if we advise people, if we are providing the optimal advice, we are likely to fail. And here are some graphs demonstrating this. This is the optimal offer. And we ran experiments with hundreds of people. And this is the average they were offering. This axis is the improvement made by our uncle, the mechanic. And you can see that people's average offer without advice is very far from the optimal offer. Now, what happens when we provide people with the optimal advice? What happens if we tell people, here you should offer 0, and here you should offer 1,000? So now we get better results, but still we are very far from the optimal offer, okay? So this calls for a different solution, something we call suboptimal advising. Instead of providing the optimal advice, we will provide a different advice, an advice which is suboptimal, okay? And ideally, what we want to do is to have something that will take as an input a possible advice, and then will predict the probability that this advice will be accepted by a random user. Okay? If we can do this, then we can provide the advice that maximizes the product, which is the probability the advice is being followed by the user, and the value of the advice if followed. Okay? But this will also require predicting the influence over future advice and also predicting what the user would do if not following the advice. So this is like kind of an utopia, right? This is the ultimate AI in terms of suboptimal advice. We are not there, but we are very close. And I will demonstrate some of the solutions we currently have for this. So one solution we have is a solution that is trying to trade optimality and intuitiveness. What the thing we are trying to do here is to determine the optimal advice and then determine the most intuitive advice. And this can be done by observing people or by using peer design agent technologies where people are actually programming their strategies into autonomous agents, or we can build a behavioral model for our users. And then we can use the distance between these two as a metric for how much we should deviate from the optimal advice. So here is an example with the car buying. We said that here, this is the factor by which the mechanic is improving our car. We said that this area is the most confusing for people. The optimal solution here is very non-intuitive to people. So we can construct suboptimal advice that converges to the optimal advice whenever we are very far from a factor of 2, and when we get closer to 2, we substantially deviate from the optimal advice. And here you can see the results when using such advisor, such helper. So this was with the optimal advice, okay? And this is with the suboptimal advice. We managed to get very close, not very close, but closer to the optimal average buyer's offer. Okay, so this is the offer we really want to make, and this is by how much we managed to convince people to get to this offer. Okay? And you can see here also the expected profit of users. The green one is with the suboptimal advice. The red one is with the optimal advice, and the blue one is with no advice. You can see that we substantially improve things for our users. We also used it in other domains. One example was the birthday paradox. We asked people to guess what is the probability that out of a party of n, a group of n people, 2 or more will be celebrating their birthday on the same date. This is also very confusing to people because the probabilities, well, they doesn't align well with people's mind. So we are using the same approach of the distance from what is intuitive to people, and we managed to improve, to reduce the average absolute error of users substantially. Okay, so a second challenge is trading user satisfaction and benefit. We have two terms here, user satisfaction and benefit. We are used to think that if the user is making a lot, if the user's benefit is substantial, then the user is very satisfied with the system. But this is not necessarily the case. And I will give you an example. So we took, I'm skipping this slide, we took the car purchasing game for a repeated setting. So in a repeated setting, the effectiveness is measured over the long term, and users get to see the actual outcomes. So we need some different designs for this setting. And we came up with two advice generation methods that are both using suboptimal advice. However, they differ in the goal. So one is trying to maximize average performance, and the other one is trying to maximize user satisfaction. And the first that is trying to maximize expected performance is actually starting with might seem to be a highly intuitive advice for people. And then it gradually shifts to the expected benefit maximizing advice. So again, starting with something which is very intuitive and slowly shifting to the optimal advice, okay? And the second one is trying to maximize user satisfaction, and here we rely on the notion of regret, which is very common in experimental economics. We're trying to calculate the regret of people from not using the advice that we provide them, and then we are normalizing the user regret for different world states, and we are then weighing the different regrets according to the underlying probability of outcomes and a beta function that somehow aligns with what Kahneman and Tversky showed us about users' perception of losses and gains. And in terms of user profit, we can actually see in experiments, again, with hundreds of people, that the first method, which was offering this gradual improvement towards optimality, managed to improve average profit of users substantially compared to providing the optimal advice and providing the advice according to the second method. What is more interesting to see is that if we check user satisfaction, so we always ask users, are you happy with the system? Will you recommend the system to a friend, or will you use the advisor, the system, again? And we can see here that it is actually the second method, the one that is based on regret principles, actually, despite of the small average, the relatively small average improvement achieved, managed to gain the greatest satisfaction of users. And it is the first method that actually, well, did better than providing the optimal advice, but not as good as the second method, okay? So this is a very important principle of understanding the difference between user satisfaction and users' expected profit or users' expected performance. And it means that we should understand this principle and possibly develop or come up with different designs depending on what we're trying to maximize, okay? And also, just to summarize this part, the things I've told you about so far. So the chance of having the user following the advice is critical for determining which advice to provide, and also intuitiveness of the advice plays a key role in advice acceptance. And we have several papers that deal with this issue. Most of them are at AAAI. This is just one of them. I had another one earlier, but I think I've skipped it, so never mind. But there are many papers summarizing these ideas. Okay, so another challenge is the challenge of nurturing autonomy. So we are used to a helper that is fully autonomous, that can do whatever it wants to do in order to maximize the user's profit or user's satisfaction from the system. But this is not necessarily always the case, okay? Because optimal choices may result in poor actual outcomes because outcomes are a priori uncertain. Think of me as a virtual investor who wants to invest your money. So you're giving me money and I make the investment on your behalf and I'm going to invest in airline stocks. And suddenly, boom, September 11, what happens? All the airline stocks fall, crashes, okay? And the user is dissatisfied. So what can the user do? The user can terminate the use of the helper, the autonomous helper, or the user can limit the autonomy of the helper. Instead of giving the helper all his or her money, he will give the helper just a portion of the funds available to her to invest. And this means that the autonomy of the helper is being constrained or reduced. So this is essentially the situation we are considering. This is just one example, but you can imagine where it goes from here. So the user has a pile of money here, and on each period, the user decides how much money out of this pile she wants to give the autonomous helper, so the autonomous helper can invest this money in stocks. And then, based on the return obtained, we move back all this money plus the gains to this pile, and the process repeats over and over again. Okay? So if the user was fully rational, then the theoretic optimal strategy would be to pick the stock with the maximum expected return. The problem is that stocks that offer a very high expected return are often very risky stocks, right? So just to provide you with an example, if we have stock A that produces a 100% return and a 0% return with an equal probability, and stock B, which is very safe, it produces 40% return, then stock A is the one associated with the most or the highest expected return. This is the stock we want to invest in. And ideally, if we invest in stock A, ideally we would run into a sequence of successes, and even if there is a loss at some point, no harm done, because the user is already comfortable with the system. But we just as well run into a situation where the sequence starts with some losses, and the user will decide to constrain the autonomy of the system. The user will limit the amount of funds providing the agent. So instead, what we can do, we can start with stock B, which is the safe stock, build some confidence, increase the autonomy granted to the agent, and then shift to stock A. And even if there is a loss at some point, we can shift back to stock B just to build again the user's confidence and increase the autonomy granted, and then go back to stock A. So essentially here what we are doing, we are using an adaptive approach where the agent is weighing in both the influence of future autonomy constraints and the optimality of the action taken. So if we are investing in the optimal stock, this is what the behavior of the system will look like if presented on this plane of the optimality of the choice and the autonomy level granted, which is how much money the user is giving the agent to invest. So this is with the optimal choice, the stock that is associated with the maximum expected return. We see that we start with something which is very optimal, but the decrease is very sharp. Whenever there is a loss, the decrease is huge. Instead, what we are proposing is something that is traversing this plane in a way that every time we have a loss, we shift back to the other stock, the safe stock. And this way, we get to the optimal choice, except that we get there on a different path, using a different route, a safer route to say. Okay, so for this, of course, we had to use machine learning. We cannot avoid this. This is now what everybody is doing, but we use. Okay, I will not avoid it. but here, the machine learning is very standard. We don't need much data in order to do that. We can rely on like tens of observations, which is very important. And we can come up with very good predictions for when to deviate from the risky stock to the safer stock. And we ran experiments with people comparing the agent that is always investing in the optimal stock compared to our adaptive agent that shifts between stocks. You can see here 2 sets of stocks. Each stock is different, okay? And we ran experiments with people, and this is the user profit when using the theoretic optimal advice. And this is when using our adaptive agent. You can see that the increase in the user's overall profit is substantial. This is with the first set. This is with the second set. You can also see the user satisfaction for the 2 sets. You can see that with the adaptive agent, users are really satisfied. They are like 2 times or 3 times more satisfied than with the agent that is investing in the optimal stock. And you can see here also the average autonomy level granted. We measure this as the percentage that the user is giving the agent to invest out of the total funds that the user currently have. And you see that with the optimal agent, there is no trend, and whereas with our adaptive agent, we constantly get more and more funds out of what the user has. You can also see the choice of the stock used. This is with the first set, this is with the second set, and you can see that we are slowly moving towards always investing in the best stock, except that, again, we are doing this somehow differently, and we gain more doing it this way. So finally, this is very quick, I just want to introduce you to the 4th challenge, which is developing strategy summarization capabilities. And we have a visionary paper at the coming AMAS. It is called Agent Strategy Summarization. Essentially, what we are saying there is that there is a missing capability in AI-based systems. And the capability is being able to present the user with an effective summary of the strategy and expected behaviors of the system under different conditions and scenarios. So for some of you, it might sound familiar because we all know about interpretable machine learning and explainable AI, but we are suggesting something a bit different, something that might seem complementary to explainable AI. Because in explainable AI, what you want to do is explain a one-shot decision in retrospect, something that already happened, and you want to explain to the user why you made this decision. What we are proposing is something very different. We want to provide the user with a cohesive description of the behavior an agent is likely to exhibit, ex ante. And this is very important. It is important whenever you want the user to understand the strategy of an agent she's working along with, or whenever the user has several alternatives and he wants to choose one of those, or when the user needs to determine the level of autonomy to be granted to the agent or approve a strategy of the agent. You have it quite often. And this is a collaborative process that involves both agents and people. And in the paper, you will find some general designs and components that should be in such designs. And you will find all kinds of directions for techniques that can be applied for doing this, and potential domains and test beds for this, and evaluation methodologies. And if interested, please go ahead and read this paper. So to conclude, many new challenges in developing next-generation autonomous helpers. In many cases, it is worthwhile to deviate from what we used to call optimal up until now, especially in repeated interaction, but also when the advice is very non-intuitive or difficult to explain, and of course, many additional challenges to pursue. So that's it. Thank you.
situations.
Thank you for the great talk. I'm not very familiar with the work, so I just ask some questions that I'm curious. For the stock problem, I guess we usually assume that there are unlimited resources from the users or from the testers that you can always take from the bank of yours. Whatever. So if there is a limitation, will it be different, like using these policies?
Yeah, so actually there is a limitation. I mean, at some point you may lose all your money, right? But I don't think it will be surprising to say that most people kept some money aside. Nobody wanted to lose everything. And by the way, this is part of the whole thing. If the agent is optimal, and the user is granting the agent the maximum autonomy, then at some point the user will lose all of her money, right? If you have a poker ball that is working for you, and now you just got this bot, and the bot is now putting all your money on a specific move, you will be scared to death. Nobody wants this, okay? And this is why building the autonomy is important. This is the issue there.
Okay, and another question. It looks like to consider the intuitive of the people's choice is kind of like a step backward. Try to find a workaround way so that people can accept. So how would it compare to a more aggressive, like persuade the people to accept your first option?
Persuasion is something that complements everything that I've just shown. Because in persuasion, you're trying to explain to the person why the optimal advice is optimal. But in many cases, the optimal solution is very non-intuitive, and explaining the optimality of this solution may take a very long time. Like, try to explain my mother this paradox of buying the car. She will never understand this. I mean, I will actually need to go through the math with her. And for most users, it's simply inefficient to do this.
Okay, thank you.
Okay. So, two quick questions. How much money do you end up spending in order to demonstrate the results for this experiment?
With Amazon Mechanical Turk, you get to run experiments with thousands of people by spending cents on each experiment. So actually, I have a PhD student that was trying to see where is the point where people will not be willing to work for the amount of money we're giving them, and we were looking for the most tedious and boring task for them. So it was finding words in a crossword puzzle, and people were willing to work on this for an hour and a half for 20 cents. It doesn't make sense, but you can actually find there people that are doing this mostly for the interest in doing this, not necessarily for the money.
Yeah, but in the stock experiment, you had to actually pay the profit to the person so that the person really felt he was investing his
own money. We pay them a fraction of the profit. We don't actually tell them, here is $2,000, now start investing this. I don't know, you really need a lot of money for this.
And my second question, did you try to distinguish between people that are risk-aversive and people that are risk-takers or gamblers?
That's a great question, and ideally you really want to do this, but the things we have been developing are for the general population. It's like you don't have the luxury of repeated interaction with the same person over and over again, except for some of the examples that I've demonstrated. And in this case, you want to develop something which is very general, that regardless of who is playing, your expected profit will be maximized or expected satisfaction will be maximized. But again, if you do have this option for repeated interaction, then definitely you want to do some user modeling and integrate such concepts into design.